Let's get started. And if we're going to talk about high-performance computing, then the first thing that we need to understand is what is high-performance computing? And you could ask ChatGPT about that and it would give you a very good answer. And I did ask ChatGPT about what is high-performance computing, and it told me that it has high processing power. I think we would agree with that. It has high storage capacity. It has high speed, high capacity networking. It has high data analytics capabilities. The other thing that we can think about, what are the features of an HPC system? And some of those things will be, there will be some kind of massive parallel processing. There will be some kind of large-scale data handling. And we are usually interested in scalability for high-performance computing systems because there is a huge cost in designing and building a high-performance computing system, and you don't want to be stuck with delivering just one size of the system. We want to be able to scale it and to the customer that we are serving for a given installation. Nowadays, most high-performance computers will have some kind of heterogeneous specialized hardware in them. And when we talk about some of the specific HPC systems that I have worked on, we'll understand why. The main reason for that is power consumption. We could not get the performance that we need from high-performance computing using just CPUs. It wouldn't work because we would then need huge power generation plants. Typically, there is a very advanced software stack in a high-performance computing with many different layers. But before we dive into the details of high-performance computing techniques, how to program them, etc., I think that's very advisable if you are considering working in any area that you try to understand what's the market size for that technology, so that you know what you're going into. Are you going into a niche market, or are you going into a mass scale market, right? So if we look at the HPC market size, and this is not a science, it's an art, there's lots of speculations on this, but some sources will say that the current market for, in 2022, the market for high-performance computing is 36 billion, and there is a projection for about 50 billion by 2027. If we have a look at some other predictions, the number can be anything between 40 billion today and 62 billion in 2032. So it sounds like to be a very good size market to work on. And if you look at still other predictions, the numbers can go up to 100 billion in 2033. I just given you several different sources to give you a sense that different people have different estimates for how big this market is going to be. Okay? But let's compare that with mainframe market size. Some of you may not have talked much about mainframes. Mainframes are still a thing and are a big thing, because organizations that have to have a computing system that never fails rely on mainframes. So your airline tickets, the processing of your grocery store, purchases, etc., they run in mainframes. The mainframe market is smaller than the high-performance computing market. So something about 3 billion in 2029. So high-performance computing is much bigger than mainframes. But now, if we look at the graphics computing size, the expectation is that by 2032, the graphics computing size will be 145 billion, and that was before the explosion of the use of graphics for AI in the last wave or the last hype around AI. So this number could potentially be much bigger. Now, if you look at the data center market size, we have an expectation of 600 billion by 2030. And this is one of the markets that's predicted to grow the fastest. Okay? So we are talking about one order of magnitude bigger than the HPC market. Okay? So if you want to really jump into a market where there is lots of growth ahead and there will be lots of investments, data center computing is much more important than high-performance computing. But then, if you want to look at cloud computing, the prediction for the cloud computing market is that by 2032, it will be $2.3 trillion. Okay? So if you want to go in an area where there really will be tons of jobs and lots of things to do, go into cloud computing. Okay? So this might sound strange for, go ahead.
How are you differentiating data center and cloud?
Aditya is asking how I differentiate data center and cloud. I'm not. They are. These are the market analysts doing that.
So it looks like the growth in data centers is about the same as the growth in GPUs. Is all of the new growth in data centers GPUs?
I don't believe so. Just look at what we do. Only a small fraction of what we do can be done in GPUs, right? Think about all the apps on your phones. They are using traditional data center capability. They are not using GPUs. Think about the number of people around the globe that are going to start using apps just the way that you do. They are not there yet. Right? So my expectation is that the data center growth is not GPU growth. And my expectation is that the GPU growth will be larger than what we have in here. Okay? But, you know, so why am I coming here to teach a course on high-performance computing? To tell you that high-performance computing is a niche market. Because you need to know what you're getting into. Okay? And if you take the companies that are producing hardware for high-performance computing, usually high-performance computing is their play toy. It's their little sandbox where they can do lots of new things that they cannot do in their mainstream processors. And that will be the main topic of this course. High-performance computing is a wonderful area to explore new things. And those new things sometimes may migrate later to large mainstream processors, and sometimes they just die out. They are not adopted. So there is another thing that people are talking about, that is high-performance computing in the cloud or high-performance computing as a service, right? So this kind of merge the two now, and that's why it's difficult to differentiate all the markets, right? Because as you know, an installation for a high-performance computer is very expensive, and not only for the computer, but for the cooling, the energy that you need, etc. So for a number of high-performance computing problems, it will be better to use someone else's infrastructure. So there is a new book that just came out this year from a number of colleagues from Brazil, actually, that's a collection of papers and essays about high-performance computing in the cloud. And if you look into the web, just a quick search, you're going to see that there's quite a bit of talk about high-performance computing on the cloud by a number of large players. So this is something that if you are going into high-performance computing, my recommendation is that you should pay attention to. So the next question is, okay, we talk about what is high-performance computing, what are the features of HPC. The other question is, what is HPC for? What HPC does, right? So if you take a traditional slide from, this one came from Xilex, you're going to see the kind of usual suspects for the use of high-performance computing. You're going to see things like molecular dynamics, oil and gas, weather and climate, financial, etc. But if you look a little bit closer, you're going to see that there are very innovative uses of high-performance computing as well. It's becoming more widespread. The use is becoming more widespread. And if high-performance computing in the cloud becomes a thing, it's likely that we're going to have even more applications using it. So some interesting things, like you can see from the European Commission, high-performance computing for agriculture production. Agriculture actually is being revolutionized by technology, right? You can find about high-performance computing in manufacturing and in healthcare. So there are a number of new areas where we are looking into high-performance computing that we need to be paying attention to. There is high-performance computing in finance. Most of the automatic trades that are done these days are based on high-performance computing, and there are specific programming languages, specific installations of high-performance computing that are dedicated for computing finance. And high-performance computing in simulation engineering is also a thing that we see a lot these days. So the next thing that we need to talk about is how we measure HPC. How do we try to stack them up? And here the story is a little bit sad, because we need to talk the truth. The metrics that are out there are very unsuitable for the tasks that we want to do. And this has been recognized even by some of the people that have created these metrics. So if you are just looking from far at high-performance computing, you may be hearing people talk about the top 500. And they make headlines, they appear, in the press, etc. So sounds like being in the top 500 and being on the top of the top 500 is a big deal. And if we look over the years, what I did here is just take the top 500, and I start in 2013, and I just put the flags of the countries where the installation is present. It's not the country that necessarily manufacture the computer, but for the case of China and the US, their computers are made by their countries. And you can see that over time what happened is that there was a period where China was dominating the top 500, and actually the US was falling down, and if you were around the US at that time, that was described as a crisis. Because suddenly now the Chinese has faster computers than the US is going to lose its edge, etc., etc., etc. And so there are answers to that. And we're going to talk specifically about some of the computers, such as the Summit computer that raised to the top of the 500 in 2018. And the story keeps going. And but let me just go back one slide so that you can look at the last year. And I don't have the last year here. I did not bother to go and get the 2022 numbers. But we have Japan now on top of the 500, or at least it was until recently. So before we get too excited about who is in the top of the top 500, we need to start talking about what the top 500 means, right? What do you need to do to enter into that list? And all you have to do is to solve one problem. And the problem that you have to solve is this benchmark called HiPEAC. And what the HiPEAC does is just does a matrix vector multiplication. Okay? So there are lots of limitations to the HiPEAC. So first of all, it has limited representativeness. It's a single benchmark. It focuses on the number of floating point computations per second. But as we know, for many of the real computations that we need to do, we need to access lots of data. HiPEAC doesn't. The ratio between computation and data access in HiPEAC is very different than the ratio that you'd find in real applications. So there is this optimization bias that happens. So in any kind of system, in any kind of economy, you give people a reward function, and they're going to deliver what you ask it for. Okay, so you ask them to do dense matrix vector multiplication fast, they're going to do it. So there is a story about, remember the Chinese raising to the top of the top 500? This was with a machine called Taihu Light. And Taihu Light is a machine that was designed to be very fast for LINPACK, because they wanted to be on the top of the top 500. Okay? So the machine looks strange when people look at that. The ratios between the amount of computation, the functional units the machine had, and the ability to access memory was very odd, compared with for people that were experienced in designing such systems. So Taihu achieved 93 petaflops at the time in LINPACK, consuming 2.4 megawatts less power than the Tianyan-2, which is the previous machine that was in China. There is a different benchmark that's called the conjugate gradient benchmark that has a different ratio between computing and data access than LINPACK. So what the conjugate gradient is doing is this, this computation here, but it's a sparse computation. So this is a sparse matrix vector multiplication. It uses a sparse triangular solver, and it does these vector updates. And what basically it's computing is global data products, dot products. We're going to talk more about dot products used for matrix multiplication in another lecture this week. And it uses this local symmetric Gauss-sided smoother. So when this benchmark is run in that machine that's in the top 500, it achieves 0.3% of the theoretical peak performance. 0.3%. Okay? So 99.7% of the capability of the machine is not being used. Why? This machine was designed to be on the top of the top 500. Now, if you look at the Summit machine, that is the machine that was the answer to that from the US. It's a machine designed by IBM together with NVIDIA. It achieves 148.6 petaflops in LINPACK. It only gets 2.9 petaflops for the conjugate gradient. It's is at less than 2% efficiency. Okay? So the US designed machines are not doing much better. There's another benchmark that's created by my friend David Bader, who is now in the New Jersey Institute of Technology, and other colleagues. The idea for the Graph 500 is that it has two types of problems that it solves. The idea here is that you are processing graphs, and you can generate those graphs to have different characteristics. So the idea here is that you can change what you do with your benchmark through the generation of these graphs. But basically, the Graph 500 solves two problems. One problem is a breadth first search, and the other problem is a single source short paths for all pair of nodes in the graph. So this is the kind of the advertising for the Graph 500 in the top of the web page. And if we look at the top 10 in the Graph 500, what they are measuring here is giga-traversed edges per second. So instead of focusing on floating point operations, they are focusing on how quickly you can process these graph connections. And another metric that people often use is the spec HPC. that SPEC is the Standard Performance Evaluation Corporation, and that's their HPC benchmark. I need to make a disclosure. Until last year, I was in the board of directors of SPEC. I was the only academic sitting in the board of directors of SPEC. But as you're going to see, I'm not going to show any bias here, because as we look at the HPC in SPEC, so those are the application areas and those are the application names that you have there. And what you're going to see is that this benchmark is very, very biased towards scientific computing. Most of the problems in this benchmark are problems from physics, cosmology, astrophysics, etc. And they are very similar. NVIDIA is a very active participant in the SPEC HPC group. I have good friends from NVIDIA that are there. Not surprising, NVIDIA is at the top of the SPEC HPC results report. So this is just to give you an overview of the different ways in which you can measure performance in a high-performance computing from where I stand. I'm sure that there are other ways to measure all that people use. And if you are working with a specific HPC installation, the question that you should ask is, what it's for? What is the problem that we need to solve? And we should measure performance for that problem. Looking at any one of those benchmarks only makes sense if the problem that you are trying to solve resembles this. So let me try to get someone's name here. Let's see. Korosh, go ahead. Is Korosh here? No. Lucia Pons. Where is Lucia? Lucia, why do you think that we need benchmarks?
Because benchmark allow researchers from different places in order to compare their work, so it makes comparison easier. Because if I use the same benchmark as other places, it eases the comparison.
That's a perfect answer, because the point is, the benchmark is only useful for comparing, right? If I need to compare with another installation, right? But the benchmark is useless for what I wanted to do with my machine if what I want to do with my machine is different from the benchmark. So my research area is actually not in high-performance computing. You may be surprised that I'm teaching this course. My research area is in compilers, right? And one of the things that I tell my students all the time, you need to read your benchmark program. You need to actually see what your program is like and what it does. And I give this recommendation for you in any area that you work. Never take a set of programs that someone else has compiled and use it blindly. You need to know what each one of those programs does and how it does it, to decide whether it's relevant for whatever is the technology that you are working on and how it affects that technology. Does not take long. Sometimes, depending on the benchmark, a couple of days, just staring at the code and reading the structure of the code will give you a much better sense of how your technology is performing. Okay? So that's what I want to say about benchmarks. Any questions at this point? Yes?
What do you think of like very well-established benchmarks that then maybe influence also what type of research is done and that influence the direction of optimization, for example, in compilers? You know, if you very much understand the benchmark problems and tune your compiler towards these problems, maybe you don't do something useful for the general case that's not like meant by that.
What's your name? Jonas. Jonas, this is an excellent, so the point that Jonas is making is that benchmarks influence what compilers do, for example. They also influence what architects do. And this is a very unfortunate thing that happens. For a number of companies and many cycles of development, the name of the game is to tune for spec CPU, right? The same way that, this story that I told you about these researchers and developers in China designing their machine to do well for one benchmark, this is done across the world in many different companies, where the way you're going to be seen in public is how well you perform in these benchmarks. So this is human nature, right? If you are measuring me some way, I'm going to try to do well in that way. So there is a huge distortion in research and in development because of these benchmarks that are accepted. So we can talk offline and you can ask me about the things that we discover about, for example, the spec CPU benchmark when we got involved deeply with the development, right? And that's very unfortunate, but I think that's human nature. We want to do better than our competition, and the only way to show that we are better than our competition is to do well in the metrics that are used to measure what we did. Any other questions or comments? Jonas, that was a very good comment. Thank you. So before I continue, I want to do something here. I hope that you don't mind. Let me give you very precise instructions. There is a pile of paper that I'm going to give here to each one of the person in the front row. You take the first one, and you pass the pile in the same way back, and everybody does that in this row. And then what we're going to do is you're going to write your name as clearly as you can on that piece of paper, and in the order in which you are sitting, okay? And what I'm going to do now, I'm going to take pictures of you so that I'm going to try to remember your names in the future lectures, right? And if you have any issues with me having your picture, just talk to me later and I'll make sure to erase that picture or to not have you there. So look at me so that I can see your face. I promise that I'm not going to be able to remember everybody's name, but I may remember some of you. So can you look at me, please? Good. No. So in terms of also giving you tips about teaching, right? You feel much better in this classroom if I know your name. It will be very hard for me to know all your name because we only have a week. But if we are together for a whole term, by the middle of the term, I will know all your names. And instead of getting a random list and calling someone randomly, I would be able to just look at you and call you by your name. You're going to feel that you belong in this classroom. Okay? So think about that whenever you're teaching. Okay? It's a two-way thing. You need to feel that you belong. Okay. So while you're doing that for us, we'll first summarize what we have talked about so far. And what we have talked about is that we try to understand what is HPC. We look at the features of HPC. We talk about the market size of HPC, and we establish that the HPC is a plaything, right? It's just a toy for large corporations. We have seen that the applications of HPC are no longer only the traditional applications. We talk about the different ways in which HPC are measured, such as the top 500, the HPCG, the GRAB 500, and the SPEC HPC. So that's what we talk about so far. So what's coming next? There are a couple of things that we're going to be doing for the rest of the time that we have together this week. The first thing is we're going to have a tour of HPC programming, and we're going to cover just a sliver of what we can do in HPC programming, but I'll do my best to cover 3 books in one lecture, right? So those are the 3 books in which, and this is the part of this course where I had to go and prepare for, and I'm pretty sure that you're going to show that what I'm giving you is a very high-level overview of what HPC is. Then we're going to be started, for the rest of the week, I'm going to be bringing you my own view of those things that we can play around with HPC. Remember, I told you at some point that HPC is an experimental market, right? Where you can try new things. So over the years, my research group has been involved through connections that I have with industry in pretty much all the top 500, all the computers in the top of the top 500 list in the US. So here you see, this is me with 2 of my master's students at the university saying that the world's fastest supercomputer contains University of Alberta technology. That happens when IBM delivered the Summit and Sierra computers together with NVIDIA. And this was in June 2018. The computer was announced at Supercomputing 2018 in Dallas. And if you were to go to the IBM booth in that fair, and you'd go to the place where they are explaining how the compiler works and how they got the performance that they got in that machine, that slide that's being used to explain it was produced by me. So it was these 2 very smart master students in my group that figured out how to get really high performance from GPUs in that machine. So this is one of the papers that we produce. I'm going to tell you much more details about this paper. This paper is in your collection of handouts during the week. Then if you go a little further back, we have Sequoia, which was ranked as the fastest supercomputer in the world. That was in 2012. And again, Sequoia is the Blue Gene Q machine from IBM, introduced a new technology that is hardware-supported transactional memories. It was the first processor that was delivered anywhere to have that hardware support. My research group was invited to evaluate the software, the hardware support for transactional memory in that machine. So we published this paper in PACT 2012. We received the Best Paper Award. My student, Matthew Godde, who now works for Mozilla, is one of the SpiderMonkey developers, won also the gold medal in the student research competition for the work that we have done in transactional memories. I intended to give a lecture on how that work came about. One of the things that I'll be doing here, I'll be telling you lots of stories. Because my hope is that you not only learn about technology, but you get a sense of how those things come about. How do we go about setting up a collaborative research between industry and academy where we have actual real results? So then if you go back to the Blue Gene L, this is October 2005. We also have a paper on PLDI 2006 that this is about PGAS, Partition Global Address Space Programming Language. It's another way of programming HPC that we haven't talked about yet. We have done work both with UPC, that the Universal Parallel C, and with X10, that was another language that was developed by IBM for supercomputers. We have, in that computer, we also deliver this restructuring of data structures. We call it forma, where initially we could take an array of data structures and convert into fields of arrays. And later we could also take any kind of link-based data structures, a graph, a tree, and convert into arrays of fields as well. And it was some very clever compiler techniques that allow us to do that. That technology is delivered in all the IBM commercial compilers since it was ready around, I think, 2010. So IBM had this PERCS project that was a cute name for something that they coined that was the productive, easy-to-use, reliable computer systems. And that was around 2011. And it was delivered in this project called Blue Waters that was delivered to the National Petascale Computing Facilities in University of Illinois at Urbana-Champaign. So for that work, for that computer, what we worked on was with the X10 technology. And again, I'll try to have a lecture on that. As you can see, I have much more material here than we have time. I'm not going to be able to tell you all my stories. But I hope that we can cover some of the important ones, and I'll take questions from you either in the lecture or anywhere else when we are hanging out during the week, so that I can tell more of some of those things that we have done. So we have several papers that are related to this PERCS project that is, and some quite interesting techniques in these papers about how you distributed work, and because that's a serious problem when you have a large computation facility and your problem may change the amount of work that it has to do in different places over time. So how do you adjust to that? We have worked on that quite a bit as well. So any questions about what we're going to do next? Or any comments? Or you don't like this at all? Okay. So one of the things that I want to mention here is, how did this come about? How come that me, a professor coming from Brazil originally, working in Canada in the West, end up involved with the delivery of the fastest computers in the world in the United States, which are paid by the Department of Energy, the Department of Defense, etc. How does that happen? And in my mind, it has to do with circles of trust. What happens is that if you say, what you need to do this kind of work, you need to establish relationships. And you have to have people trusting you. So in my case, what happens is that this started in between 2000 and 2001, when I moved to Canada in 2000. And I had friends at IBM T.J. Watson Research Center through my postdoc, which I did at the University of Delaware with Professor Guangao. I had just moved to Canada, new professor. I had no connections in Canada whatsoever. I reached out to Eric Altman, who is a well-known researcher at T.J. Watson, and I told Eric, I'm now in Canada. I'm intending to work on compilers. IBM has the largest compiler team in the world in Canada. The compiler team at Markham was at the time responsible for delivering all the commercial compilers for IBM worldwide. I said, I need a contact there. And I was kind of picky, and I said, Eric, I don't want 5 contacts. I only want 1. And then Eric responded and said, there is only one person with whom you should talk. It's Bob Blaney. And so he introduced me to Bob Blaney via email. We start a conversation, and then he said, do you have a student? And I had my first student at the time, who was a master's student, Kit Barton. I sent Kit Barton over to IBM for the summer, and I was lucky. Kit Barton was a really good student. Kit Barton eventually became responsible for all the backends of all the compilers for IBM. He still works in IBM today. He's now doing quantum compilation. But through that connection, we establish a relation of trust. And then when you have a relation of trust, you can expand by now being in contact with other people that are in the trust circle of the people with whom you establish that relation of trust. We have this funny human thing. We tend to trust people that are recommended to us by people that we trust. So trust can be transferred in that way, okay? And if you don't believe me, there is an excellent talk from, I think, 2007. Some of you may know that Linus Torvald does not talk much. But he has given a talk to Google about Git. And in that talk, he talks about the circles of trust. Why is Linus Torvald interested in circles of trust? Because he is responsible for approving changes to the Linux system. And he's not going to let anybody do disapproval. So he has to trust someone. So this idea of the circles of trust comes from his talk, where he talks like, if you trust someone and then you trust that person to judge other people, you're going to start trusting the people that that person also trusts. Okay? So I want to suggest that. So now that we have covered the beginning, we have established what our road ahead is, it's time for us to start with the actual content of the course, right? And as I said, the first thing that we're going to do is talk about how to program HPCs. And then after that, we're going to embark, starting tomorrow, in this journey of talking about different things that I have been directly involved with, related with HPC systems. So let's talk about HPC programming. Again, I need to move my mouse before I can click. It's one of the features of this little system that I have here. So someone already mentioned in one of the initial questions that I asked about the idea of a programming model when you are programming any computer, including a high-performance computing system. And I would like to expand that idea to say that there are two models that we need to worry about, and one of the problems is that we often mix them, or we don't really see the distinction between them. So one of the ideas is the idea of the programming model, and the other is the idea of the execution model. And in my mind, what happens is that application programmers should be working with a programming model. So application programmers should have a view of the machine that tells them, for example, that this machine is a bunch of processing nodes with some local memory connected through an interconnect network, okay? Or they may have a vision of the machine that this machine is a machine that has some kind of shared memory system that I can access any position of memory at any time from anywhere in the machine. And there are several other such programming models. So this is the model that the programmer has of the machine. How does the programmer sees the machine? There is another model that is used by compiler writers, by runtime system writers. Is a model that probably the architects have in their minds as well. It's a much more detailed model. It's a model where you now worry about the size of caches, how many layers of caches you have. Pretty much you follow all the path of the data through the system. And I think it's important that we distinguish between those, because bringing too much of what should be in the execution model to the program model will create these specializations in the program that will make the program less portable. On the other hand, if you are trying to write a compiler or a runtime system that is too general, that's not looking at the specific system where the program will gonna run, you're gonna miss opportunities to make the execution time faster or to consume less memory or less energy. Like you lose optimization opportunities. Yes?
I was wondering what is the main difference between a programming model and a model of computation?
Joseph, thank you for the question. I don't really know what you mean by model of computation.
For example, if I have an application which is doing a certain task, this task can be divided in smaller tasks. And I got the, how to say, the relationships, the tokens, which is the data which is circulating in this application. And in my team, we work in this with this paradigm, the data flow model of computation. And from that, we can generate a multi-core program. So,
okay, I know what you're talking about now. Okay, so yes, you can abstract the machine. So, for example, in the data flow model, and you can try to have just a model of what your task needs to do. But then, if you're gonna create a program for that task, you're gonna have to map that into a programming model. The programming model gives you a model of how the machine works. So you can have a model of what the application needs to do, which can be quite abstract, right? And then, but then if you're gonna run it in a machine, you have to have a model of how the machine works. Okay? Whenever we are writing a program, even if we don't think about it, we have a programming model in our mind. We have a model of how the machine works. For most of the undergrad programming courses, the model is the von Neumann machine, right? The model is a sequential execution, right? But it is a model that we are following. So one of the programming models that is very broadly used and is still broadly used in high-performance computing is the message passing model. And for that, we have the message passing interface. And the idea here, we're going to be trying to summarize in a few slides what is in this book that is using MPI by Group, Lusk, and Skillion. And the idea of the MPI programming model is that you have processors that are represented in this slide by circles, and then you have address space. We tend to refer to the memory modules as the address spaces that I can access. And these processors are connected through a network. So as the name says, if I wanted to get access to data that's not in my address space, I need to send a message to the processor that is responsible for the data that I need and have that processor do something. Now, MPI has evolved over time and became much more sophisticated. The initial idea is that I could send a message and ask that processor to send me the data, right? Or I could send a message and ask that processor to store data somewhere. We can do much more sophisticated things with MPI today, but that was the initial model. But most machines are not like that. Most machines are more hybrid. So it's more likely that I have something like this, where I have an address space and I have multiple processors that can access that address space. So in this case, what we're going to do, the programmer will not going to have this model in mind. The programmer is still going to have the original MPI model in mind, and we're going to have a layer that's part of our software stack that will map that MPI program to here. So we can make a decision in our implementation, for example, that only the core 0 of each one of these nodes will be responsible for communication, for example. That's totally our decision in implementing. It should not affect the way the program is written at all. So we always have this concept that there is the programming model, which is an abstraction of how the machine works. And then there is an implementation layer that will implement this MPI for a specific machine. So what would be the minimal message passing interface that we can have? It will be something like this. In one part of the address space, there will be a portion of data. And I will issue a command in that processor. I'm going to execute a function in MPI that will be a send function. And the send function will have an address that says where the data starts. We'll have a length that tells perhaps in bytes how many bytes I need to transmit. And will tell me what is the destination of this message. So I'm sending this message, for example, to the node 5. And there will be a tag. The tag is used to order the receiving of the messages on the other end. And then on the receiver side, I'm going to issue a receive function. The receive function will also have an address that says where should I put that data when I receive it. We'll say the length. You see that the lengths here are different, right? From the sender to the receiver. Because the receiver is actually saying what's the maximum length that I'm going to accept, because I allocated a buffer to receive that data and I don't want to exceed that buffer. And then it's going to say the source. And the source, I have a wildcard. I can say MPI any source, which means that I'm receiving data from anywhere in the machine, not from a specific node. And the tag also, I have an option to say MPI N tag, which means that I'm open to receive any message, not just a specific one. And then I have in the very end there the active length. And if you're not a Fortran programmer, this may look a little bit strange, because in Fortran, the return addresses are also what look like an argument to the function. So the active length is actually a return value, and you can have multiple return values, and they are going to appear in the list of arguments of the function. But that's a Fortran quirk, and you see most of the work, most of the textbooks on MPI be based on Fortran, and that's for historical reasons. So there are some issues with this model that we need to sort out. The first issue is that how about if I have different representations for the same type in different parts of this machine? If I only specify the number of bytes that I'm going to transmit, and I want to transmit 4 integers, and in one machine the 4 integers, the integers are 32 bits, in the other machine they are 64 bits, I have a problem. Specifying the number of bytes is not a good idea. The other problem is that sometimes I want to send messages that are not contiguous. I have a gather-scatter kind of situation. And the other problem is that how do I order messages that come from libraries, for example? I have no control over the libraries. I don't know what the libraries are doing when they are talking with my program. And the last issue that I have is that I may have multiple groups of processes that I want to work. I might want to partition my machine in such a way that I have different partitions in this machine that I'm going to work with. So how do we solve these issues? First one, for the different representations for the same type, we're going to replace that basic send that we just learned about with an MPI send, and the difference is that the MPI send will have something called a data type. So I'm going to say, for example, that I wanted to transmit 4 integers. I'm not going to say that I want to transmit, 16 bytes. For non-contiguous messages, I'm going to allow the user to define data types, and these data types can be non-contiguous. So remember, in my sender message, now I have a data type. That data type can be any type that has been defined by the programmer, including types that are not contiguous in memory. To order the messages from the libraries, I'm going to create this runtime or dynamic contexts, where I can determine what's happening during execution at execution time. And for multiple groups of processors, I'm going to create that thing that appears in the end there, that's a communicator. And we're going to talk a little bit more about that soon. So this communicator will combine the group and the context that I'm going to use. So now we have the MPI receive combination. That is, I have an address, the max count. Remember, the receiver always says, what's the maximum number of elements that I'm willing to receive? And the data type. So those 3 describe the receiver buffer. So it's pretty much specifying that I have created this buffer where I can receive data. The source will give me the rank. In NPI, you call, instead of saying the number of the process or the processor, you say the rank. That's the terminology in NPI. So you say the rank of the source in the group that's specified in the communicator. So I have now multiple communicators. So I don't look at my machine as an entire machine. I may look at my machine as a group of several different machines. And then the status is a return value that will tell me the actual size, the source, and the tag of the message that I have received. So there is a default communicator in the very bottom of the slides, the NPI communicator word, that it will define a single context that contains all the processors in the systems. So if I wanted to use the machine as a single monolithic machine, I'm not interested in partitioning the machine in several different segments or areas, I can simply use the default communicator from NPI, and I'm using the entire machine. Any questions so far? Okay. So you have some initialization functions that you have to have in NPI. So for example, you have NPI init, you have NPI communicator rank, and you have the NPI communicator size. So those are all initialization functions that you have to run in the beginning of an NPI program in order to initialize the communicators. So this error is a return value. Again, remember in Fortran, the return value appears as if they were arguments in the function. It either will say success, or it will say that there is some implementation-specific error code that you are trying to initialize NPI, but something is wrong. This is the default communicator that contains all the processors in the machine in a single context. This is the rank of the current processor. Is a return value. So in the initialization, the system is telling me what's my number. That's basically my process ID. And when I do that initialization, what the system returns to me is how many processors I have in the system. Because remember, I'm going to write a program that may be running in many different machines, and my program may be, depending on the number of depending on the number of processors that I have, I may be doing different things with my program. I want to know how many I have. So let's look at two examples of operations in NPI here. One is a broadcast operation, and the other is a reduction operation. So let's first talk about broadcast. If I'm doing a broadcast, what I have is that NPI call on the top there, that's an NPI broadcast, and N is the address that I want to broadcast from. One is the count of how many one is the count that tells me how many items I'm going to broadcast. This is the type that I want to broadcast. So in this case, I'm broadcasting one integer. This is the process that contains the original copy that I'm going to broadcast to all other processors in the system. So what broadcast does is exactly what it says. It's going to take that single integer from the address space of that processor and send to all other processors in the system. Let's talk about the reduce operation. A reduce operation is an operation where you do the best way to explain reduction is, for example, to think of a sum. Let's say that you want to sum a large number of values. What you can do, and we can do this in this room here, I can get every two people that are together to combine their numbers, and then they're going to pass on to the next pair, and then to the next four, etc. So you do this 3 reduction usually. So how can I do a reduction here? First, you have the source address. In this case, is in a computation of the number pi. So my current value of pi. The other is the reduction is the result address. It will be in the address pi. The number of items that I communicate in this reduction. The type of the items in this case is a double precision MPI value. The reduction operation, in this case, I'm doing a sum. So this reduction will be the sum of double precision values, the rank of the processor where I'm going to have the result in the end. So what the MPI is going to do when I call the reduction operation, each processor will combine its value with the value of its neighbor in terms of the rank numbers. So 1 and 2 will combine their values and get the sum of their values. 3 and 4 will combine their values, and 5 and 6 will combine their values. In the next step, now we have 2, 4, and 6 containing the sums of their pairs. So 2 will now combine its value with 4, and 6 will combine its value with 0. So now I have 0 and 4 containing the partial sums, and now 4 and 0 will combine the results, and 0 will contain the final result. So that's how a reduction operation is done in NPI. Any questions about that? Yes?
You told us we could use custom data types. For example, MPI double precision, does that result to a number of bytes? How would we go about putting in the definition of a custom data type? Could we just, for integers, say 4 instead of that macro?
Yes, so the MPI double precision is a default data type in NPI, and the size of it will be implementation dependent. Okay? If you define your own data type, you're going to be defining the size of your data type, and NPI are going to use your definition. Okay? So, yeah.
I'm wondering what's the typical overhead on figuring out which node you should get your value from?
All such questions about overhead is implementation dependent. Okay? Because, for example, I can implement NPI on top of a shared memory machine, and the overhead might be much lower than a machine that's connected through a network. So remember, we are distinguishing here between the programming model and the execution model, right? In the programming model, it's very hard for you to know what the overhead is because it depends on the machine that you're running and depends on the software stack that you have under you.
Can you control order of reductions to control order of operations?
I love that question because I don't know. It's the first time that I have an opportunity to say, I don't know. Okay, we can look into the book and see if there is any way to do that, or look into the MPI documentation. I don't know. I am not an MPI programmer, by the way. Okay, the idea here of bringing you these different programming models is not that I'm expert on them. I want us to have an overview of how we can program these large machines.
Could you talk a little bit about how the rank is determined for each of these operations?
So Aniket, so the rank here is just the number of the processor. Okay, that's all that is. Yeah, it's just a sign. There is a system to assign that. I just checking the time. We have 3 minutes. My class is always, well, we're gonna take that with questions. That would be good.
Sorry, I have a question. How do you define the neighbor? How do you define the neighbor of a node that are directly connected?
So Giovanni is asking, how do you define the name of a node, right? So the name of a node here is the rank, and the communicator will define the name. So far we are only using the MPI default communicator that says, I take all the processors in the system and I consider them to be a single machine, and I can name them however I want. You can define your own communicator, okay? And then you can name them however you want. You can just tell MPI that you need a communicator that contains 16 nodes. And you can let the implementation define which nodes will be part of that communicator. And if your implementation is very good, it probably will pick one region of your machine where communication between those nodes is less costly. So all these questions about performance are are given to the implementation. Because the implementation is whoever is implementing MPI in your machine is the person that understands how the nodes are interconnected, how the network works, etc. Make sense? So it's a flexible programming model in that sense, right? So if you just hear about NPI, you think, oh, it's just a message passing system. It's very inefficient. Actually, it has evolved to be a very efficient system, and that's why it's still broadly used in the high-performance computing arena, especially in the national labs in the United States. There was another question somewhere? Or is it already sorted out? Okay, good. So the next, and maybe we're going to just start this and maybe we're going to pick up here tomorrow. The next thing that MPI has resources for is something called stencil computation. So a stencil computation is a computation like this one. In this case, I represent a 5-point stencil where you have 1 point, and the value that you compute in that point depends on its 4 neighbors. So the number of points on your stencil always includes the point that you are computing. So if you have to compute this for a very large number of points in a parallel machine, most likely you're going to want to divide this data in regions and give a different region for each one of the address spaces where the computation is happening locally. But of course that creates a problem, right? The problem in the boundaries. So one thing that I could do is to divide it this way. So remember, rank just means the number of the processor that's doing the computation. So I could do this division, and I would have, in this case, 3 processors computing, and each one is responsible for one area. So most of the accesses that that processor is doing are local. However, as the picture illustrates, I'm going to have to talk with my neighbor to get values in the boundary. And those communications will be expensive, right? Because in MPI, the idea is that I have to send a message to another processor to get the values. So that was the division. So what I can do is to create this thing called ghost points. So instead of attributing only the points that are going to compute to my node, I also attribute the neighboring points that are the ones that are computed by a neighbor, not by myself. And those are called the ghost points, and they create the ghost regions for the computation. If I do a 2D decomposition like this, now I have more processors doing the computation, then I'm going to have more issues with the neighbors, but I can create these ghost regions now that are 2D ghost regions. So those are techniques that are well known and have been well known for a long time. So in order to do these decompositions and to map data to processors with different ranks, MPI has this virtual topology that is called the Cartesian decomposition. And what you do, you simply ask MPI to give you a domain decomposition, and you can specify how you want it to work, or you can let MPI do the decomposition however it wants. You just say, I have this data, I want to decompose in a 2-dimensional way, and I want you to assign the different regions to the different processors in the machine. The idea is that if you have a very good implementation of NPI, the decomposition will be such that the neighboring regions will be in the right place for the topology of the machine. So now that we have this 2D decomposition, the question is how a process will find its coordinates in the grid, because when you do the computation, you need to know where you are in the grid, right? So you declare this array of dimensions with you, and then you have this other declaration that says is periodic is a question that will say whether your decomposition is periodic or not, or whether it wraps around or not. So in this case, you say that the first dimension is 4, the second dimension is 3, This is defining the size of your decomposition that you're going to do. In this case, I declare is periodic 1 as false. It means that the rightmost and leftmost of these areas are not connected, so it does not loop around. And also the top and bottom are not connected. And see the versatility here, I can declare each one of those dimensions to either wrap around or not. That's what the property is periodic is. And then I have this parameter called reorder, that whether I can tell NPI that it can reorder my regions however it wants, or I can say no, don't do that. Okay? So in this case, I'm telling NPI that it can find a good way to associate a process to each element of the composition. The number of dimensions here is 2. And now I can simply call an MPI Cartesian create to create my decomposition. So if this is true, MPI can assign processes to the elements of the decomposition. I'm very conscious about the time. We're going to stop here. I like to stop in the middle of something, because then when we start tomorrow, we can pick up where we left.